In this video, I'll present the use of a couple of different data sets that are prepared and distributed by the Center for Near-Earth Object Studies of the Jet Propulsion Laboratory at Caltech. It's interesting to see what objects are out there, what objects might be threatening Earth, and the kind of thing that people do to assess the risk of impact events. And also in general, this is an interesting lesson or exercise in finding and using data, particularly numeric data, which is an important skill these days. The first data set that I'll demonstrate is called the Close Approaches data set, and it has both past and future objects that have passed by the Earth or are expected to pass by the Earth based on astronomical observations. And the idea is it's basically around what objects are going to come closest to the Earth. There's two useful or two principal choices that can be made when one tries to find out data about close encounters, close approaches. One of them is the time frame, recent past, um, right about now, plus or minus 30 degrees, a year in the future, a year in the past, all future, etc. And then the other thing is how far away the object passes. LD stands for lunar distance, which is 200 and something thousand miles, the distance from the Earth to the Moon. And an AU is an astronomical unit, the average distance from the Earth to the Sun. So these range from reasonably close encounters all the way up to 18 or so million miles away, which is not really a close approach, but it's still recorded, still detected and recorded. In this table, you can answer a lot of interesting questions. One, for instance, is what near encounters are we expecting in the near future, within the next 60 days, or perhaps before the end of this calendar year? And we can ask for maybe just as a guess as to what the small group of those might be. We can ask for all the objects in the next 60 days that'll pass within 5 um, lunar distances from the Earth. And I'm going to um, confuse I have to do. Sometimes you need to do a refresh to get the tables correct. And I'll go with 10 lunar distances in the near future, and it tells me that there's 16 entries, or 16 objects, 16 entries in this table. There's 16 objects known that are going to pass within 10 lunar distances in the next 60 days. It's possible to go ahead and, well, we can also show all 25. It's possible to just scan this and see the objects. Here's one that's going to be slightly past the end of the year, but it's still within 60 days. So we can look at these dates. There's an encounter coming up on November 5th, today, but it's going to pass within 2.68 lunar distances. So that's actually a reasonably close encounter, but the size of that object is not very large, 9 to 20 meters in size. Noticeable, but not a terribly threatening size. Threatening size objects would be 100 meters or more. Anyway, the question I set out to answer is what's the closest encounter? So once I have a reasonably short list of objects that will pass fairly close in the next 60 days, I can quickly get the answer I want by clicking on this and finding and sorting. I've clicked on the up or the down arrows, and I'll sort by the minimum distance. And the answer to the question I posed is yes, before the end of the year, November 8th, 3 days away, there will be an object that'll pass within 1.27 times the distance from the Moon to the Earth. So it'll actually be outside of the Moon's orbit. and it's a somewhat substantial object, but the distance away is fairly large. So sometime before the closest approach that we'll all have between now and the end of the year is 1.27 lunar distances, and the hard to understand name of that object, 2019, the year it was first observed, UM12, and there's the size of it. So that's the use of one table. The other table, the other data set that's available, is a risk, the Sentry table, which reports the impact risk. And the impact risk is often, for public consumption, is measured on the Torino scale. But for most of the it's easy to understand. It's a very simple scale. Most of the time, everything's zero, so it's very boring. A more scientific scale with a little more detail is something called the Palermo scale. Palermo scale takes into account the energy of the object, which is closely related to its size and how fast it's moving with respect to Earth, and the chances that it's going to hit the Earth. So the Palermo scale is a true risk measurement in that it takes into account how likely something is to happen times the damage that would be expected. Damage, energy, directly related to the size of the object. So Palermo scale is a risk scale or a danger scale because it does take into account the damage possible and the chances that it will actually happen. So the Palermo scale, for trying to figure something out perhaps, we might want to just take all the objects, any object that's ever been observed, and objects that only have a Palermo scale bigger than -4. An object that has a Palermo scale of greater than 0 actually presents a risk bigger than random occurrences from all other objects. If in the table right now, there's only objects with a Palermo scale greater than -4, which is only 1/10,000th of the background risk. So these objects are not particularly scary. Just to answer one particular question, what's the most dangerous object that's out there right now? And it's the notorious 29075 1950 DA, which is looking to pass by the Earth in the year 2880, which is still quite a while in the future. It is, however, an enormous object of close to a mile in size, and it does have a 1 in that e to the -4 is a 10,000th. So this is about 1 in 10,000 chances that it will hit. And using a complicated formula, this size object and its potential damage combined with this probability gives a Palermo scale of -1.42. So this is well below the threshold when this object would be of actual interest. So we don't really have a lot of impact event risk at this time. There's another way to sort this table, and that is by sorting by probabilities. And we'll sort from one can sort from the highest probability, which is in this case is 5 in 100, or 1 in 20 chance that this thing will affect the Earth. And that's the highest probability event, 2010 RF12. So the most likely impact known right now is 5 times 1 in 100, 5 in 100, or 1/20th. And the diameter of this object actually is 0.007 kilometers, so it's only 7 meters in size, which is a pretty heavy object, but in the grand scheme of things, it's very small, and therefore its Palermo scale is actually almost 100th of the other object I just showed you. So that summarizes the use of these tables, and I will stop right there.